Good morning, guys. Chapter 2.2, limits involving infinity. But before we get into that, what I'd appreciate is if you hit pause and you try to do these first 5 problems. And once you're done, come on and I'm going to work them out. Okay, so if you hit pause now, work them out. I'm going to continue to work the problems. Now, the first one is limit as x approaches -2. Well, remember what we do is we automatically substitute in to our function to look and see what we got. We got 3 times -2 squared is 4 minus 5 times -2. That gives me 12 plus 10. Oh, this limit is 22. Really nice, okay? And we move into number 2. We put a 1 in there. And when we substitute that in, we get 0 on the top, and we put a 1 minus 1, we get a 0 on the bottom. That means find it, okay? Find it, massage the function a little bit. You got to find it, and because it's a rational function, what we did was we factored. And we said there's a common factor of 3 in the numerator, so what do we got? We got x minus 1. Bottom is a difference of squares. We got x minus 1 times x plus 1. Oh, lo and behold, there is that rascal. That has given us that 0 over 0. There's our common factor in the top and the bottom. After we reduce them out, well, we resubstitute in. And when we resubstitute our 1 in, we get 3 over 1 plus 1 is 2. Looks like the limit is 3 over 2. Then we get down to number 3. And it's like, aha! I get it. Woo! That equals 1. Remember, you dirty, rotten scoundrels, what we need to do is we need to plug in the target value first. So we have the sine of pi over pi. The sine of pi is 0 over pi. Ooh, that limits 0. Okay? Then we come to the limit as x approaches 0. I might need a little bit more room there. Not a lot, but what we see is we get that. The sine of 0 is 0 over 0. Yep, that means find it again. And we see that crafty little critter that we had before. We see a sine value here approaching 0. I'm thinking some people are looking right in here with the shortcut and they're seeing that right out of the blocks. They're seeing what it is, maybe like, I don't know, a half. But what I'm going to do is I'm going to move this and I'm going to break this apart. I'm going to see a fraction times a fraction. And we know we want that sine 3x there. Okay, we got a 6x on the bottom, so I know I need a x there. And I can see that 6 as 2 times 3 times x. And I can nest the 3x over here, leave my 2, put a 1, because 2 times 3x, yeah, that's still my 3x. Then I can take the limit, and I know this limit, as it goes to 0, I know that limit's 1 times 1/2. Oh, just like I said, that limit's a half, okay? The other one we can do here is down at the bottom. And that annoys me when I do that. And what we're going to do is we're going to direct substitute in there again, okay? And when I direct substitute in, I'm going to get that. What do I get? I get 6 over 0. Whoop, I get a number over 0. What does that mean? That means the limit does not exist, okay? Now we're going to be looking at limits at infinity. We know that means a vertical asymptote, okay? And we will use that for directionality later. But let's just say we were looking for the limit as x approaches 2, let's say from the left, of 3x over x minus 2. Okay, well, either way, I don't care. I'm still going to plug that 2 in the numerator. I'm still getting close to 2 from the left. So here's your number line. So if I'm coming in from the left, 0's here. I'm thinking 1.99999. That's what's going in here, right? So regardless, if I plug that in, it's going to be super duper close to 6, isn't it? Super close to 6. And if I put 1.99999 minus 2, this is going to be very small negative number, right? So what is a constant dividing by something getting smaller and smaller and smaller? It's getting bigger and bigger and bigger, and a positive over a negative, ooh, that limit would be an asymptote. That would be going down on the left side, okay? So we're going to use these limits at infinity or limits involving infinity, and that answer dictates to me does not exist, but it's just showing the direction the graph is going, okay? So we're going to come into the next one here. Limits involving infinity. Ooh, yay. Here we go. Basically, we are talking about asymptote behavior, okay? Couple things we're looking. Two things are going to happen. Either x is approaching plus or minus infinity, or the limit value, the y value, is approaching plus or minus infinity. Okay, we're going to look at both of these. The first one we're going to look at is as x approaches plus or minus infinity. As x goes to plus and minus infinity, remember, that is end behavior. Okay, that's end behavior. Knowing that, well, what could be happening to the function as x gets super, super big? What could be happening to the function? Well, there's really only two things that could happen. Okay, so as x gets super, super big, y gets super, super big. Okay, that could happen. And in that case, there is no limit. No limit. Limit does not exist. And basically what we're looking at when that happens, as x gets super, super big up here, as x gets really, really big, and y gets really, really big, well, that happens a ton of times. Example, polynomials. And then the question, oh, what's a polynomial? Oh, they could be y equals, could be maybe x squared, could be maybe x cubed, could be maybe x to the fourth, or a conglomeration of all of them added together. Well, remember, my end behavior of a polynomial, they were really boring. Squares either they opened up or they opened down. So here I can see as x goes to infinity, y goes to infinity, or in this case, as x goes to infinity, y goes to negative infinity. Or I could have my wiggles and squiggle. Oh, that's a crappy wiggle and squiggle. I could have as my powers get bigger, remember, even powers and behaviors are the same. They're either both going up or down, like here. Odd degree and behaviors were opposite. Right side goes up, left side goes down, or right side goes down, left side goes up. Either way, the graph is going up. It's growing. It's getting bigger and bigger and bigger. It's not approaching a specific number. Therefore, the limit does not exist. Well, what else could be happening as x gets really, really big? Well, y could be approaching some value c, some specific value. And in that case, the limit would actually equal that c. And the limit would exist. And it's that actual value y is approaching. Well, what the heck does that mean? Well, an example of this would be, we've done quite a few. We'll do a lot more today. Think rational functions. Rational functions many of them have horizontal asymptotes. And it happens to be that horizontal asymptote happens to be y equals c. My graph is getting snug as a bug in a rug. It's not ever getting to it. Way out at plus and minus infinity, it's going up or down, or it's flattening out. Okay? There are also some special cases that can happen here. Okay? If it's a horizontal line, special cases I'm going to write. Well, let's say I have horizontal line. and let's say my horizontal line is going to be y equals some value. I'm going to call it a, just for fun. Well, I can see my graph if I have a horizontal line, okay, and this is going to be 0, comma a. So I can totally see my limit as x goes to infinity. Y is approaching that a value, okay? My limit would actually equal a, special case, on the horizontal line, okay? There's a couple more special cases. Another special case, let's think about sine x, or y equals sine x, or cosine x. What happens there? Well, think about that. We pulled all our values off the unit circle, didn't it? The sine, the range of the sine always went from 1 to -1, didn't it? And the cosine always went from 1 to -1 as well, right? So think about your sine wave. I should color code these. Sorry, I'm going to get rid of that. Get rid of that. And I'm going to make here, I'm going to say my sine started at 0 and went right? And it just kept on a going, and it kept on a going, and it never stopped. So I can think of, as x goes to infinity, what's my y going to? My y isn't going anywhere, okay? There's no limit here. No limit. Another way to state it, does not exist. I like that better because it's faster, it's shorter, and I'm lazy. Okay, so that limit doesn't exist. Or if I had the cosine, which is basically just kind of a shifted sine, I'm going to do that guy in green. Well, that went kind of went like that, and that kept bebopping and bebopping and beep like that, right? What did that do? That oscillated between 1 and -1. The same way the sine went from 1 to -1. The limit does not exist. The reason it doesn't exist is because it's oscillating between two values. Where's it going to hit? I don't know. That just depends where I hit in the unit circle. The bigger x gets, remember, that just means the more and more and more and more times you're going around the unit circle to stop at a place. Okay, so that one doesn't really do anything. We also have maybe y equal tangent x or cotangent x. Now those graphs looked a little bit different because my tangents went like this, right? And they just kept, and I had asymptotes in there. Well, what happens as x goes to infinity? Well, my graph just repeats, okay? Cotangent's basically the exact same. The only difference is crumb. I think it goes like that. Either way, I might have my graph back asswards. I'm trying to think now. So my first 0 should be a pi over 2. And as I go quadrant 1, I go up. Yeah, go back. So either way, that's a repeating graph. So there's no limit here either. I want to take graph, no limit, or does not exist. Okay, that one doesn't really oscillate. I think of that one as a repeating graph. Okay, it's a repeating graph. So that's why as x gets really, really big, I'm just going through another cycle. I do go to infinity, but I go to many, many, many specific values, okay? And there was one other special one here. That's another oscillating function, yet it did have a limit at infinity, okay? We looked at this one yesterday. We looked at the limit as x approached 0, no. We did look at approaching 0, but let's approach infinity here. What happens as x gets really, really big of something like sine x over x? Okay, what did that end up approaching as x got really, really big? Well, it oscillates as x gets really, really big. This is going to always be between 1 and -1 no matter where I'm at. And if I divide that by really, really big, what is a constant divided by really, really big? This limit went to 0. But it oscillated, okay? And this was not a horizontal asymptote because I was always something, and as x got bigger and bigger and bigger, this value of this fraction got smaller and smaller, and it was approaching 0, okay? But it wasn't a horizontal asymptote because I was always oscillating positive to negative, positive to negative. So I was going up and down across. It wasn't a horizontal asymptote. Well, so that is taking a little look at all these. Sorry, I write so big on here. I don't really mean to do that. And the next one, you're going to have just as many things to write down. But those are what could happen as x gets really, really big. Well, what happens is I can have no limit polynomials. I can have a particular limit, which is my horizontal asymptote, okay? I have some special cases of a line. Well, y equals a, the limit of a constant is the constant as I go to infinity because it's a special line. I can have no limit with a trig function because my function just continually oscillates between two specific values, and as x gets big, it just periodically, that's why they call them periodic functions, they just run through the same exact cycle of values every 2 pi units. Tangent does the same thing. It runs through the same cycle of values every pi units. So same with the cotangent, okay? Doesn't really, it's not oscillating, that one's repeating. Or as x goes to infinity of this specific special function here, because the sine of x is always between -1 and -1. I should have these flip-flop, shouldn't I? The sine is always between -1 and 1. And when I divide a constant by something that gets really big, it gets closer and closer, and it gets really small. It's never quite getting there because it's always a value. Every once in a while it will, in this particular instance, because the sine can equal 0. Okay, what's the next thing that can happen? Well, let's say x is approaching a particular value. Okay, c, this is going to be a finite number or a finite value. What do you mean a finite value? Well, I'm talking maybe x is approaching 2. Doesn't matter if I'm approaching it from the right or left side. X could be approaching 3. It's a finite value, okay? It's not infinity like the example before. Well, what could happen? What has happened to us as we've been taking limits as x approached a specific target x value other than infinity? Well, what happened is we could get that limit y was approaching a specific value of b. What are you talking about? Well, if I'm talking about y approaching a specific value, let me come back to the beginning right here. Okay, y was approaching a specific value, and the limit was something. Okay, it came out. I used substitution, and I got it there. Substitution worked. Substitution worked. Sometimes, let me come back here. Sometimes we had a hole in the function, dear Liza, because we got a 0 over 0. But what did we do? We kind of massaged that function by factoring it, getting rid of that 0 over 0 because there was a hole in it, and we found it, and that limit still existed. So I'm going to say sometimes substitution worked, sometimes there was a hole, and we needed to work, spell right. We had to work more to get it, but the limit actually equaled that value of b. Because y was getting closer and closer, I plugged in a c and I got out a b value some way. Sometimes it was a hole, sometimes it wasn't, and the limit was that b value, my y value. Well, what else happened? Sometimes I didn't hit a specific value, something like that. Sometimes y just got super, super big positively or negatively. Well, what the heck did that mean? As I approached a specific value in the middle of the graph, and my graph spiked up or down, what happened? I had a vertical asymptote. And that vertical asymptote was at x equaled that c value that I was approaching from the top up here. And in that case, there was limit did not exist. There was no limit. Okay? It was unbounded behavior. Whoa. And that's where I say we can use the limit as I approach c from the right side or the left side. I can use my limits saying whether if y is approaching positive infinity, I know it's going up, and if y is approaching negative infinity, I would know that that graph is going down. We're going to use this analysis as I approach a specific value to show if the graph is going up or down on either side of a vertical asymptote, okay? That's going to be more tomorrow. The main thing, and I just want to fill these notes in, but as soon as we're through these notes, we are going to be looking very much at, whoa, come on. I'm losing my marbles here. We're going to be looking very much at this as we're approaching a specific C value, horizontal asymptote hunting, okay? Any limit that involves infinity, whether I plug infinity in or I get infinity out, okay? It's hunting for asymptotes. We're going to mainly be looking for horizontals today. So what did we do? The limit existed, happened. The limit didn't exist here because we ran into a vertical asymptote. We also had our y value. Sometimes it approached two different values. And when it approached two different values, again, that limit did not exist, okay? Because the left was unequal to the right. That's why that limit didn't exist, okay? So these are approaching two finite values on each side. When did that happen to us? Well, one example, I'm going to say some piecewise functions that happen. Step functions. And the biggest step function we have is the greatest integer function. What is the greatest integer not greater than x? Okay, so we approached a particular value. Sometimes our graph went straight up or straight down, didn't exist. Sometimes we approached two different values, a different one value from the left, a different value from the right, meaning our graph did not come together. What else happened? There was a special case in here too. Unique, we looked at a very unique situation yesterday, and I'm going to put that on here. one unique situation that we just kind of straight up need to really know. Y approached, it oscillated between values, and I'll show you what I'm talking about by that. And in that time, the limit again did not exist. The reason it didn't exist because it was this is a big word, oscillating behavior. In that oscillating behavior, the example I'm going to give you is what was the limit as x approached a specific value 0 of the sine of 1 over x. And what happened here, as x approaches 0, the bottom gets really, really big, right? So all that did was it controlled where we were on the unit circle. And if you think about when we saw that graph yesterday, okay, it looked really nice. And then as I got right here, it just went, yeah, and then the further away it went, because as x got close to 0, this fraction, 1 divided by small, is big, really big, which meant I kept going around the unit circle, but I was always stopping somewhere between 1 or -1, and it got so big, it just kept hammering back and forth in there. And it really wasn't any specific place at 0, because that number I'm taking the sine of was getting bigger and bigger and bigger and bigger. And that was oscillating behavior, okay? Main thing we're looking at today is we are looking at limits as x approaches positive or negative infinity, okay? I'm going to graph it on the TI here in a second. You could graph it on there. I'm just telling you, 100% expectation, you know what this graph looks like. You could hammer this graph out. And this is the mother of all rational functions. And from there, I have a branch in the top, and I have a branch in the bottom. I also had vertical asymptote in the end, horizontal asymptote in the end, okay? And as the limit, when I came out, I can read it because this notation is the right hand end behavior, the right hand end behavior. Okay, so as x goes in, what is the limit of 1 divided by big? As this gets bigger and bigger and bigger, 1 divided by a number gets bigger and bigger and bigger, equals smaller and smaller and smaller. Okay, which means it's slowly approaching 0. And I'm also looking at this through a different lens as I'm taking a positive, because this is a positive infinity, it's a positive over a positive. I'm approaching 0 from the positive side or the top. Just like I said, I'm coming down, and I can look at my graph there. As I approach negative infinity, well, this is over big, but negative. Well, that goes to 0, and it's a positive over a negative, so I'm coming to 0 from the bottom. Well, just like I said, as I can see, I can come across, it's getting, as x goes to infinity, this graph is getting closer and closer and closer to 0. It's never going to hit 0 because I'm always taking 1 divided by something right here that's really big. It's getting smaller and smaller. As that's a negative number coming in, a positive divided by a negative, I'm going to approach 0 from the bottom, okay? Just remember that. That's the little mother function we had there. The limit in this case for these, okay, my limit value, that's annoying, limit value is the horizontal asymptote. Okay, where's my horizontal asymptote? Oh, it's at y equals 0. My limit value was 0. Sometimes from the top, sometimes from the bottom. Okay, no big deal. That's what we're looking at on that one. Well, what happens if I move into the next example here? Okay, definition. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either as x approaches infinity, it goes to a number, or as x approaches negative infinity, it goes to a number. Yes, we do have functions that only have possibly a right hand or a left hand end behavior. They don't really have to have a limit existing on both sides with a horizontal asymptote. Think of a exponential function. In this case, this is the only limit that would equal b, and in this case it would be 0. As I went to infinity, it would be infinity. Okay, so I don't have to approach the horizontal asymptote on both sides all the time. There's lots of different functions. Hence the reason why you need to know your parent functions. Okay, so as I'm coming along, what I'm going to do is I'm going to look at this, and we can look at the graph. Okay, I can show you the graph as I'm approaching infinity of -2 plus 1 over x. Boom, there it is. Where is it? Oh, looks like I'm approaching -2 as my horizontal asymptote. I can get that super easy thinking about this, okay, because I'm going to plug it in. If I plugged infinity in, I really have -2 plus 1 over huge big. Okay, well, because this is getting bigger and bigger and bigger, it's actually going to 0, which means -2 plus 0, this limit would be -2. Now also, kind of think about this too. I'm adding a very small yet positive number here. I would technically be approaching 2 from the top of 2, because -2 plus a very small positive number is a little bit on top of 2, just like my graph shows me, a little bit on top of 2, okay? A little bit more than 2. Look at this next one here. The limit as x approaches negative infinity. Well, what happens to a really, what happens to a really big number as, what happens to any number, whether any negative number, when I square it, it turns positive, right? So here I'm going to get 1 over positive big, okay? And I don't even know if I have this one graphed in there. I don't think I do. So this bottom's getting bigger and bigger and bigger, right? Constant divided by something getting bigger and bigger and bigger is going to 0. Why did I put that positive? Well, because I'm squaring it. So I'm going to have a positive over a positive, which would mean I'm coming to 0 technically from the top, okay? And sometimes they want to know if you're hitting the top or the bottom. So what does this mean? This means I have a horizontal asymptote at y equals 0. Okay, next one here, it's really boring, it's really tough. How do I plug infinity in here? Well, what is this? What is this going to be? What is going to be 3 times infinity squared minus 5 times infinity? I don't know. Seems like it could be 0 because you're subtracting infinities. Well, not really. What's happening here, the limit's infinity does not exist. What? How are you picturing that? Look at this function. What kind of function is that? Ooh, that's a parabola, because the biggest power is in x squared. There's no fractions in there. Which way is it? Oh, it's concave up. So no matter where I graph it, as x goes to infinity, my y is going to infinity. It's kind of a crafty little one to think about, okay? So that limit, because it's going up and not to a specific value, the limit does not exist. We're going to come to this next one, number 5. Okay, think about this. Limit as x approaches infinity of the cosine x over x. That parent function, cosine x, what is the cosine of a very big number? Well, it just depends on where you're hitting the unit circle, doesn't it? It could be anywhere. As this number gets bigger and bigger and bigger, this numerator is going to be outputting some number between -1 to 1. And I don't know where exactly it is between there, because this means it's getting bigger. It's never stopping. But I do know this will always output a number between -1 and 1, right? Now, if I do that and I divide that by infinity, what happens? A value somewhere between -1 and 1, dividing by something that's getting bigger and bigger and bigger, where's it going? It's getting smaller and smaller and smaller. It's approaching 0. Now, I just want to take a second here and I want to say, this is not a horizontal asymptote. No, it is not. Why not? Because it is going to oscillate. It's oscillating, but the limit exists. It's oscillating, and because it's oscillating and approaching something, it's not a horizontal asymptote. And I'm not really gonna, is this my next one in there? There it is. So if I took this, and let's take this out to 100, okay? It's really hard to see how much it's oscillating, but if I took this and I made this really, really small, like maybe, I don't know, let's go between 1 and, this one. This is the one I want, and maybe -1. Oh, I didn't want to do that. I wanted this one. 1. So I can see it's getting smaller and smaller, but it's oscillating. The more I jump in there, 0.5, the more I zoom in on the Y scale, the more I can see the oscillations happening. But that's why it's not a horizontal asymptote. It's always bebopping. But as X gets super huge, okay, these oscillations are getting super small. And that graph is sooner or later, it's never getting there. Okay, it's never ever getting there because X never quits. Sometimes it will be, maybe at, I don't know, pi/2. Cosine of pi/2 is 0. So sometimes I get 0 so every once in a while it will be on there, but point is, it's not a horizontal asymptote because it keeps going like this, getting closer and closer and closer to 0, okay? This next one, I want to look at the graph really. I want to look at the graph first, okay? This is a big, ugly rational function. Infinite limits as X approaches infinity. This is end behavior we are looking at. We're not looking in the middle of the graph. We're looking way out to the outside, way to the right. In this case, way, way, way out to the right because it's positive infinity. Well, let's look at this graph. Some people are going to be looking at this equation already, this function, and they already know what the limit is. Well, let me pop that little bugger out. Let me get to my next graph. And how we graphically found our horizontal asymptotes, remember, is we went menu, we went trace, we traced the graph, and we went, say, to 100, 0.61. Then we went to maybe 1,000, 0.6018. Then maybe 10,000 and bigger, 0.06. And then 100,000, it gets bigger. What does it look like it's approaching? Looks like it's approaching 0.6. 0.6 or 0.6. Or maybe 0.6. Another way to say 0.6 would be 3/5 now, wouldn't it? Reduced. Well, how the heck does that happen? Well, it happens because we're horizontal asymptote hunting, and there is an algebraic way to show this. And what I want to do is I'm going to zoom up, and I do this a little bit different than Mr. Brugink did this. I do this different. I don't even know if our book does it this way, but the algebraic way in a rational function algebraic way to find the limit as x approaches infinity of a rational function, what we do is we divide all terms by the largest power of x in the denominator. What? Yeah. We divide everything by the largest power of x in the denominator. And I can easily find my limit then. What is my biggest power of x in the denominator? It's an x squared. So what I do is I come down, and I'm going to write this all out, the limit as x approaches infinity of 3x squared over x squared plus 5x over x squared. I get a really ugly complex fraction, which really freaks people out. And it doesn't matter. And then what I do is I reduce my complex fraction. And this is so cool. This equals the limit as x approaches infinity of what? Those reduce, I get 3. Plus, I get 5 over x for that one, minus 4 over x squared. Over, those reduce, I get 5 minus, I'm supposed to be dividing by an x squared there, 7 over x. And after I do that, now I evaluate my limit, because how do you plug infinity in? It's a super ginormous number that's getting bigger and bigger and bigger. And when you take a constant and you divide it by bigger and bigger and bigger, it slowly, quickly goes to 0. This one's going to go to 0. They're never going to quite get there, but they're getting so small, they barely affect the value of 3. This one goes to 0. It's barely going to affect the value of 5, and I end up getting 3/5. And that's how I algebraically do that. I divide all terms by the largest power of x in the denominator, and then I evaluate my limit. Okay? It's really kind of nifty. And that the only time we do that is if x is approaching infinity, because I need to find those numbers over infinity that are going to 0. So when I look at this, okay, if I plugged it in, okay, what you get is you get infinity over infinity. It's kind of like, except it's not a whole, it's an indeterminate form of a limit. It's kind of represented like 0 over 0. Okay, and if I get infinity over infinity, it's no good. Infinity over infinity is not 1, just like 0 over 0 is not 1. So what we do is we look at this and we're like, oh, end behavior. How do we find end behaviors? We divide everything by the largest power of x. Do you have to write everything out like I did there? No. I can say divided by x squared, divided by x squared, divided by x squared, which will give me the limit as x approaches infinity of, well, that gives me 3 over x in the top, and that gives me 1 minus 2 over x squared in the bottom. Now I can evaluate my limit. That guy goes to 0, that guy goes to 0, and I end up getting 0 over 1. Well, what is 0 over 1? 0 over 1 equals 0. Okay, so my end behavior on that is 0. I can show that to you in a graph. Okay, there it is. My end as x goes to infinity. As I trace this little rascal, I'm going to go to 1,000, 10,000, or 100,000. Don't really care. It's getting closer and closer and closer to 0. And it is, I can get the directionality of this if I wanted to, meaning where it's coming from, top or bottom, very logically, okay? Because as this is going to 0, 1 minus something, I'm going to be taking a 0 divided by that positive number is coming in from the top. Because this is always going to be positive. It's always going to be positive. Right here, that's always positive, very small. And when I take that, I can see I'm coming in from the top because this is very small. I'm going to be positive over positive going to 0, okay? What else do we got here? Do I want to do? Yeah, I want to do this one. Okay, we can modify what we're doing. What is the biggest power of x? Because if I plug in here, I can see infinity over infinity. The reason I divide by the biggest power of x in the bottom is because I don't get confused in the end. So I'm really looking at, we can jump to the limit as x approaches infinity of, if I divide that by x, well, what do I have? I have 4x minus, if I divide this by x, minus 4 plus 3 over x, right? And then here, divided by x, I actually have what? 2 minus, I have 2 minus, minus 12 over x. Now I can plug in my infinity. As I plug in infinity, that goes to 0, that goes to 0. But what's 4 times infinity? That is really super stinking big, isn't it? So this numerator, this is going to be getting bigger and bigger and bigger, meaning it's at infinity. And if I take bigger and bigger and bigger and divide it by 2, remember this is never stopping. That's always getting bigger. And if I take half of something that's always getting bigger, I go really big, meaning the limit does not exist. I can show you that on the graph. Okay, check it out. If I go to the next one here I am. Here's my function. As x goes to positive infinity, my graph goes straight up. Okay, goes straight up, goes bigger and bigger and bigger. So what I want to do here is I want to sum this up in the next minute or so. Well, more than one, sorry. Toothpick time, get them out. Look at the last 3 examples, notice the powers. Okay, what did we talk about? Horizontal asymptote rules in Algebra 2, right? And pre-calc. What did we say? We said this limit was 3/5. Okay? Rule. Equal powers. Okay, the limit or the horizontal asymptote was the ratio of top over bottom, wasn't it? Meaning biggest power, variable of biggest power, coefficient of biggest power over coefficient of biggest power. Okay, what did we find for number 7 here? We found this limit was equal to 0. Okay, so here, technically, my horizontal asymptote was 3/5 or 0.6. Here, after we did this, when I divided it out in the previous page, we found the limit was 0. That meant the horizontal asymptote was y equals 0. What was the rule? The rule was bigger in the bottom was y equals 0, wasn't it? Okay, when we looked at number 8, it didn't have a horizontal asymptote. It was infinity. That's a crappy infinity, but the limit was infinity, which meant no horizontal asymptote. Because there's no horizontal asymptote, there's no limit, does not exist. And how did we know that? Looking at our powers? Well, we knew that looking at powers because bigger in the top was no horizontal asymptote. Bigger in the bottom was always y equals 0. Equal powers was y equals lead coefficient over lead coefficient. Okay? These bring us to what are called end behavior models on page 76. There's this cool little exercise. I think it's number 35 through 38 in the book, and it says match the function with the graph of its end behavior model. What the heck is an end behavior model? What an end behavior model is when I'm looking at number 6, okay, my end behavior model, because I'm going so big, only the ginormous, only the biggest powers of top and bottom are going to deal with how that graph is going as x gets bigger and bigger. So I can think of this end behavior model is really as f of x equals, in the end, I have 3x squared over 5x squared, okay? But remember, those x squareds will reduce, so my end behavior model is simply going to be, in this case, because my powers are equal and they reduce, it's 3/5. That's my end behavior model. Well, what that means is, what is an end behavior model? Let me come back. Let me find that little guy. Here it is. So I'm going to menu, zoom back to my standard window, and I'm going to add something here. I'm going to add y equals 3 divided by 5. Okay? So I'm going to end, this is my horizontal asymptote that's in there, and it's an end behavior model because as I come to my menu and as I zoom way out, as I zoom out, this green graph is going to turn in to the blue graph to where the further, now notice I'm way out, the further I zoom out, all I can see is what's happening. It's so, my graph is, my windows are so big, I can't see what's happening in the middle, but I can totally see what's happening at the end behaviors, and they are modeling that equation of y equals 3/5, okay? That's what an end behavior model is. So if I took my next one, my next end behavior model here, okay, I would take these. And let's say that that end behavior model on this one, let's call it different than that. Let's call it g of x. If I took those two biggest powers, it's going to reduce to 3 over x, isn't it? So my end behavior, because this is the mother of all functions, my end behavior is going to actually be 0 on that. So if I came back and I came back to that graph and I zoomed back to a standard window, let me get back to my standard window, and excuse me, and I put the 3 divided by x in the same one, as I zoom out, okay, as I zoom out, and I want to zoom way out, that, I don't know, a yellow graph is going to turn into the red graph sooner or later, and I'll zoom out far enough, I can only see what's going on way out to the right, way out to the left, hence the name end behavior model. This last one, okay, this is the coolest thing since sliced bread. This last one, I'm going to go green there. I'm going to take my biggest powers, and when I take 4x squared and divide it by 2x, okay, what do I get? I'm going to say my h of x end behavior model is going to be 2x. Ooh, what is that? That's a line with a positive slope going up, isn't it? Now this had no horizontal asymptote. It had no limit. Limit didn't exist because it was going to infinity. This one's awesome. I love this one. And I apologize for the length of this video. But now I'm going to tab. I want to add my end behavior of 2x in there, okay? And what I'm going to do, I'm zoomed out quite a ways already, you know, just to see both branches of that. But as I continue to zoom out, okay, this black line, the end behavior model that we took, just the biggest power in the top, biggest power in the bottom, as I continue to zoom out, it turns into only being able to see 2 lines. Now I'm way, way, way out. Okay, look at the scale. I'm way out, but as I go to infinity, this isn't even close. That 2x models what the other one is going to be. That's why it's called an end behavior model, to repeat that again. So if I looked at this last one, okay, what would my end behavior model for this last one, what is it going to be? Well, I can look at it in one of 2 ways, okay? I can divide everything by the biggest power and algebraically do this. I can think of, actually with limits, unless I specifically am asked to show algebraically to find that infinite limit. If I'm not specifically asked to show it algebraically, I can look at this thing, I can say, oh, I'm big in the bottom. Huh, limit 0, and I can say what my end behavior model, my model, I'm going to call it, I don't know, what do I want to call it? I'm going to call it S of x. This end behavior model is going to be right here. It's going to be 3 over x, which is modeling that same one. So if I graphed it in the same place, okay, I would see it. The other thing I would want you to do here, and people might be saying, yeah, but Kruger, why? What do you mean? You're just changing the function here. And I'm not. When I'm dividing everything by the biggest power of x and I reduce it, if you graph this function that's written in blue, don't worry about the red. If you graph this function, it will be that exact graph, tit for tat, dot for dot, all the way through, okay? And that's what the end behavior models are. Sorry this one's so long. I'm hoping tomorrow's shorter. If it's not, the next day is going to be super, hopefully short. Have a good evening.